Not seeing that email.
I just sent it, so it might take a minute to make its way through the ether.
To go to space and back.
To go to space and back, space and beyond.
It's a Savage Garden lyric, right?
Is it really? Wow, that's a very Aussie reference, Savage Garden. That is legit. Let me make sure live stream people are all good. Hey, live streamers. Hey, live streamers, can you guys hear us okay? You guys in good shape? Tell me in the chat. Hey, hello. Okay, the live streamers cannot.
I think they were joking, but we'll see.
Uh-oh. Oh, I get it. I get it. That was a joke. And he's telling me right now that it was a joke. All right, cool. So, hey, everybody. Thank you for joining us for this Hangout. My name is Eric Brown. I'm the executive producer at Coinhaber Brown. Rusty Ward, who you have been familiar with in the past, has moved on, very sadly, from the Spacetime family. He did an amazing job for 2 years, and we were so happy with all the incredible work he did on the show, and then with the Patreon. And so we sent him off with a lot of love, and he wanted us to tell you guys that he's going to miss you very dearly. So, but as we move into the rest of this year, me and my partner Andrew Kornhaber will be producing Spacetime, which is awesome because we were the original producers of Spacetime. So we're extremely excited to be back and digging in. So that's super fun. And yeah, so we're happy to do our first Hangout together with you guys. And on the Hangout, we have, of course, Matt O'Dowd. Matt, say hi.
Hi, Eric. How are you?
I'm good. Matt is the host of this time. And we have Mike Petro, who is one of the editors of Spacetime. We have Grayson Blackmun, who is the animator who creates all the incredible visuals in Spacetime. We have Graham, who is one of the writers on Spacetime. He works with Matt on some of the craziest quantum theory episodes. So, he's your man if you want to get your mind blown. We have Dean Fukua, who is one of our Hypernoverse supporters. And I have not connected up with this other gentleman who's on the line here. Sir, would you please introduce yourself?
Are you talking to me?
Yeah.
Oh, I'm Tambi.
Hey.
These other guys I think know me. So
Tambi's a regular.
Yes. Oh, okay. Yes. Tambi
Tambi's our most regular.
Tambi Barsbay.
Yes. I'm home today, so if you guys like dogs.
Who doesn't love dogs?
What is a Barsbay? I don't know. Is a Barsbay a dog? Is that a thing?
What's that?
Did you say? Oh, you have a dog.
Yeah, I'm calling it from home today. So.
Oh, sweet. Okay, so and hello to everybody on the live stream. We've got Patrick Gilmore and Jackie Lee and Stevie himself, Shannon Catalano. Hey, Shannon, how's it going? We've been emailing. Thomas Vorobjov. People are starting to drop in questions, so I want to stop running my mouth and get started here. So, Matt, is there anything that you wanted to say, just in general, to get us started before I just start throwing out questions that people are putting up?
Sure. So today is a big day for astronomy. This is one of the things that's flown under the radar. I don't know how many of you are familiar with the Gaia satellite, but this is a European Space Agency satellite designed to essentially map a large fraction of the Milky Way. It's going to look at something like 1.5 billion stars, covering something like a quarter of the Milky Way's disk, getting some insane a quadrant. Yeah, it's going to map the local quadrant. Federation space, basically, is what it's going to dim out. And it's kind of flown under the radar because ESA has a horrible press department or something, but it's going to revolutionize a bunch of astrophysics. Anyway, I'm saying this because the entire, I guess, second data release, which includes really all the interesting data, was dumped today, and astrophysicists everywhere are going psycho trying to get into this and see what crazy stuff it's going to tell us. But essentially, it's going to produce a perfect 3D atlas, including all of the velocities of stars in the local quadrant, which is going to tell us some really crazy stuff about how our galaxy formed and about near-Earth asteroids. It's going to find all of the asteroids and just a bunch of stuff that we have no idea. So there's going to be a ton of cool stuff coming out. You know, in popular media, if you see Gaia stuff, it's worth a read. Drew Rosen, who also does some writing for Spacetime, is sitting in with a bunch of the astrophysicists who are poring over the data, and he's going to try to throw together a quick episode for us to shoot, so we can get you guys the very first details as soon as possible. That's what I have to say. That's what I'm excited about right now. What's that, Tim?
What's going on with the James Webb Telescope?
That thing's currently slated to launch in the year 3000, I think.
Coming right up.
It's still going to happen. Now it's I believe 20.
Every time I see a new delay headline, I'm just so disappointed.
Yeah, it's a very complex piece of equipment, that thing. So many new technologies developed to fly with it. You know, it's so unpredictable. But now that $8 billion is invested in it, hey, there's no turning back.
Yeah, I'm just terrified somehow like Trump's going to cancel it. So
yeah.
Even as it is, you know.
So as we go here, I wanted to give Dean the opportunity to ask any questions, and also give Dean the opportunity to show off his Schrodinger's cat mugs. Dean, turn your volume on. There you are.
So Matt, I thought you would like this, right? I got this at NEAF last weekend up in New York. It's a Schrodinger cat coffee mug set.
Aww. And it's in a box, so you don't know what's in there until you open it.
It's in a box, right?
Does it come with a radiation, like some uranium?
Yeah, it comes with radiation.
So I collapsed the wave function on this one, so I got the dead cat.
The dead cat.
Right.
All right.
But they originally looked like this. You know, when you don't have coffee in them, it's just.
That's cool. Okay.
Right. So yeah, you don't know which mug you have until you put coffee in it.
I see. Okay.
Or tea,
as you did. You're a tea drinker, right, Dean?
No. I was when I was in England, but now that I'm back in the U.S., I drink coffee.
I'm still kind of confused. I grew up in a Commonwealth country, so I grew up drinking tea, but coffee is obviously much more efficient as a caffeine delivery.
Okay. Let's not get off on a tangent.
Dude, this is a chat. We're about tangents here.
So,
all right.
So you would say that the cat appears when something radiates into the mug, specifically heat.
Yeah.
Very scientific.
It was a radiation joke. It didn't land. Sometimes you just gotta throw stuff against the wall and see what'll stick.
Okay. Well, Dean or Tambe, do you guys have any questions before I go to the live stream questions?
No, I'm angry about the James Webb thing, but that's it.
Yeah. So Tambe, to really answer that, it's going to launch. And I think all the hard stuff's been built. These 6-month delays are pretty inevitable, I think. but I wouldn't worry too much about cancellation. I think
All right.
I don't think Trump would dare cancel a mission like that. Honestly,
I would hope not.
yeah.
I had one question about the Gaia data. All right, you said that it has velocity information. Is that only like proper motion, or is that does it also have like rotational velocity for like binaries?
It would have that for resolvable binaries. I mean, the resolution is really insane. I can't remember what it is, but it should have that also. So, I mean, the velocity information is so good. The resolution is so good. It's able to track changing position of stars over the few years of the observations. So not just Doppler velocities, but actual plane of the sky velocities, which is so hard to do. Which is why it's so unique. And so, for sure, binaries, it would have that too.
Okay, that's nice.
I'm gonna go into the live stream here. So Patrick Gilmore, the very first question says, "I'm still confused how the singularity, or whatever it was, at the Big Bang, got past its own event horizon. I've read things that claim it was inflation, but even after inflation, all the matter and energy in the universe was well within its own Schwarzschild radius. So what the hell, Matt?"
Yeah, what the hell? So this is a good one, and it confused me at one point too. But let me give you the simple answer. It's that simple. Is that in order to have an event horizon, you need a concentration of mass or energy. So you need, you need an acceleration due to there being essentially a differential. You need more mass here, less mass here, and so the acceleration in this direction needs to be enough that you have this essentially light speed flow of space. But in the early universe, it was extremely dense. Maybe denser than a black hole, but this density was even. It was the same density everywhere, and so the net gravitational pull in any one direction wasn't enough to produce, at least to produce a black hole everywhere.
This was
so one of
you
the
covered this in primordial black holes a little bit, I think.
Yeah. So a key point is that at the Big Bang, the so-called singularity wasn't a singularity at a single point. It wasn't that all matter that exists was in one single point. It was that all matter in a given region was collapsed to an arbitrarily small point. Okay, maybe not an infinitesimally small point, but a very small point. But if you collapse an infinite universe down, no matter how far you collapse it down, as long as you don't collapse it infinitely far, then it's still infinite in size. Okay, so it still goes on forever. You just take any given region, like for example, our observable universe, the 42 billion light year, 46 billion light year radius of our observable universe, and take all of that and collapse it to a point. But you still have infinite stuff surrounding it, and so with this relatively smooth medium, you don't have the giant gravitational well that you need to make a black hole. That said, there probably were some that were made. There were probably some regions that were overdense and did produce event horizons, and may have produced these primordial black holes, like Grayson pointed out. How's that? Does that make sense to anyone?
Pat, tell us in the chat if you have any follow-up, or anybody else. I'm watching the chat. Batusai 9K says, "In the primordial universe before inflation, would there be excessive gravitational waves that would accelerate the evaporation PBHs? Before inflation, everything was casually related." Matt, is that a related question, or is that
where is this question?
It's at the very bottom of the chat.
Okay.
Meanwhile, Patrick says, that kind of made sense, but I'm still thinking about it, which is fair enough. I'm still thinking about a lot of things.
That's a tough one.
Let's not do that one right now. Let's move on to Stevie himself, which is trying to blow our minds here. He says, if the Earth is round, then why is space-time flat?
Ah, okay.
You know what I mean?
Checkmate.
You know what I mean?
Checkmate, flat earthers. I think Stevie himself is having a joke.
What?
I would guess, but that's a good one.
It's because NASA's incredibly well funded, and they can make you think whatever they want.
Right. It's all. Yeah. Thomas Vorozhov says, "What was the motivation behind the physics of life video? Did someone just read Dan Brown's Origin and thought Jeremy England had a point?"
You know what? The origin of that video was me and Joe Hansen talking at where was it? I don't remember. And we wanted to do a collaboration, and we wanted to figure out how to do one that involved both space-time and biology of some sort, which are clearly the least connected subjects. And so we kind of stewed around of different topics. I was originally going to do something on, the origin of the ingredients of life. That how do you get these amino acids and other organic molecules? How do you set up the primordial Earth to be right for the formation of life? But then I realized it would be more fun to talk about whether our universe demands life, whether the actual physics of the situation, especially because there is work on the subject, and not just Jeremy England. He's kind of the latest guy to be talking about this stuff, but Freeman Dyson and Erwin Schrödinger also talked about the physics of life. So it's we do what we find cool.
I can chime in with a bit of a tangent on that, which is I strongly recommend the book Life Ascending by someone whose name escapes me at the moment, but it details sort of from the bottom up a bunch of really cool key evolutionary steps. And the start of this is kind of the chemistry / physics of what's required for the inception of life on Earth.
Mm-hmm.
It's a great book.
Jackie Lee has a more space industry question. He says, or she says, or he says, is it the right timing to start a space tech startup, since we can do more stuff in space? Is it time now to start a startup to do space ventures and start providing and servicing technology for space ventures? Matt?
Right now, maybe. I don't know. I'm not really qualified to answer this. I feel like there's a lot of money in building and launching satellites. I have some friends who are shifting from astrophysics into asteroid prospecting for asteroid mining. But the payoff is a way off for some of these things. But I think probably people really are starting to think very seriously about investing big money in some of this stuff that will produce insane returns. But I guess the challenge is, how long are you willing to wait for those returns? And
I mean, every sci-fi book or show is about corporations owning the solar system because they invested in asteroid mining, right? Like, people have been saying that's going to be the new titans of industry will be the asteroid miners and the transportation kings of space.
Mm.
Nick Gall says the entropy of the universe is a fairly disputed and confusing topic. When will you do an episode on entropy and the entropy of the universe?
Maybe soon. This is the stuff that Graham and I have been talking about. So I think the first thing we'll probably do is talk about the entropy and the thermodynamics of black holes. Okay, so moving on from our Hawking radiation stuff, Graham's working on some stuff on information as a conserved quantity in quantum mechanics, which will lead us into the information paradox. And then it's natural to talk about the thermodynamics of black holes, and that naturally leads, I mean, all of that stuff naturally leads to talking about the same things regarding the universe. I agree it's a confusing topic. It's really worth doing. It's really worth doing well. I think I want to do an episode along the lines of our "What is energy?" Do a "What is entropy?" episode, just because, you know, get the groundwork down. But
right,
yeah,
we've been talking about doing some of those like fundamental question episodes.
So maybe we can make use of Graham's expertise. Graham, you still with us?
I am indeed.
Okay. So did you see any questions here that are worth?
There was, yes. There's a question by Stevie himself about, do black holes swallow dark matter as well? And the short answer to that is yes. So the one of the sort of main assumptions, which I think is fairly well established, is that dark matter obeys the same laws with respect to gravity as baryonic or normal matter, and so should experience gravity in the same way as everything else. And there's kind of nothing, I think, that, you know, the fact that dark matter only interacts gravitationally is kind of all you need. There's no other interaction you have to have. The caveat to that is that in general, in order for stuff to fall anywhere, it needs to maybe lose some energy, which is normally done thermally. So if you have jets of gas and dust orbiting something that then are able to radiate some of their energy away, then they can lose some of their angular momentum and fall in. So if you have some stuff rotating around a black hole, then it won't necessarily be able to lose energy and fall in. But, you know, if you fire a dark matter particle at a black hole, it will be devoured by it.
And once it's in the black hole, it doesn't matter that it used to be dark matter. Is part of the, you know, people sometimes ask questions like, "What if you made a black hole out of dark matter?" The answer is you would have a black hole, and you would never be able to tell that it was made out of dark matter.
Yeah, exactly. So there's the there's the so-called no hair theorem, which basically says that the only quantum numbers, which is a fancy way of saying the only quantities of interest that you can detect, or that sort of uniquely determine a black hole, angular momentum, electric charge, and the mass. So apart from that, you don't actually care. You know, if you throw in a bunch of positively charged matter and a bunch of positively charged dark matter, then all that matters about that stuff is the angular momentum, the mass, and the charge. So it's kind of agnostic about the fact that it's dark matter.
I mean, that kind of ties back into, I mean, it's directly related to the information paradox, correct? Right?
Exactly what I was about to say. Yeah. Yeah, because according to quantum mechanics, you should be able to like trace the, you know, any quantum state of the universe indefinitely backwards in the past. And so if you lose information about what type of particles went into a black hole, then you've lost quantum information. Did I say that right, Graham?
Yeah, essentially, and the next step in that kind of argument is, well, if black holes radiate, then does this radiation carry some of that information out? And then that's where it gets a bit tricky, because if it's purely thermal, then it's kind of, if the distribution of radiation coming out is purely thermal, then this is the same as saying it's kind of random or thermally distributed, which means you really have maybe lost all of that quantum information that uniquely determines that stuff.
So, okay. Hold on, I want to, hold on. Dean says, on the Big Bang singularity inflation, is the assumption of an event horizon valid? Does an EH presume a space-time surrounding it? It's in the chat for the Hangout, Matt, if you want to take a look at that.
Yeah, but basically what I'm asking is, all right, so was there space-time, was there space or space-time around, you know, was the singularity embedded in space-time, or was space-time just, you know, a construct within the expansion itself?
Oh, that's an interesting question.
Right, and if because it seems to me that we identify event horizons in relation to or as being embedded, right, or holes in space-time, right, where we can't we don't have access, right? If the singularity existed before space-time, or the inflation created space-time as it went, was there an event horizon? I hadn't heard the original question posed that way before, so
Okay.
it made me ponder.
Okay. I mean, I think people probably don't take the Big Bang singularity too seriously anymore. You know, you can rewind your equations describing the expansion of the universe back to t equals 0, and that's where you get the singularity. That's where you get that the scale factor of the universe, essentially the size of the distance between galaxies, the distance between anything is 0. But you also, before you hit that point, you have a universe that's on the Planck scale, where we know that the very equations we were using to rewind fail. Okay, so we know that they're not an adequate explanation at that point. I mean, we can rewind far enough to know that, you know, we're on a crazy energetic and dense scale where you can form you know, black holes, event horizons out of the material of the universe. But yeah, I mean, we just can't really talk about what comes before that in a confident way. So how does inflation come into this? You're talking about possibly inflation after the singularity.
Well, the original person who asked the question presented it as you know, did the inflation overrun, you know, the event horizon, right, that existed? And I heard that it phrased in that way, or, you know, that there was an event horizon.
Yeah.
Like if there was an event horizon around this initial singularity, how did matter escape?
Well, so
first
of all,
or small.
First of all, even if you allow the, you know, rewinding your Friedmann equations and you get a singularity, it's not really a singularity in terms of everything existing in one point. It's an infinity. So singularity is also a mathematical term we use to describe an infinity, and it's an infinite density, but it's an infinite density that exists everywhere. And perhaps extends infinitely through space. Because you have a still infinitely spatially infinite universe that has, you know, this infinite density everywhere, or is at least approaching the infinite density, and that doesn't have an event horizon. It doesn't have a global event horizon. That sort of space, and so inflation. You know, Graham, correct me if I say anything dumb, but I don't think that you need inflation to expand that that initial state. It also may be that in fact there was no such, you know, initial state for this universe, but in fact the initial state was inflation. So the idea of this idea of eternal inflation, where the default state, if you like, for the multiverse is just an exponentially inflating space-time of, you know, possibly other numbers of dimensions, but then the Big Bang itself is when one part of that stops being that state.
I want to we're coming towards the end, so I want to keep going with questions. Professor Mayfield asks, what might gravitational wave observatories tell us about the period before the cosmic background radiation period?
So the LIGO won't see anything from before that time, but it may be that pulsar timing arrays and other kind of, if you like, you know, galactic scale observatories could. So anything that comes from before the cosmic microwave background probably comes from, in fact, the very earliest instant of the universe, just post-inflation. And the gravitational waves that will be produced at such an early time would by now be so incredibly stretched out by the expansion of the universe, essentially redshifted, that they would be, their wavelengths would be on the scales of light years. And these constitute what we call the stochastic background, which is a fancy way of saying just the lowest level rippling of the fabric of space-time across the universe due to whatever crazy events were happening way back then. But we might be able to see that by looking at many pulsars in our galaxy and watching very tiny shifts in the period of their extremely regular pulses. What can they tell us? I mean, I think this is one of the very few ways to test some of the craziest ideas about inflation. I think there are even predictions from string theory that can lead to different types of waves from that very early time. But it's not exactly my field. Graham, you got anything?
No, I don't think I necessarily have anything to add to that. I mean, yeah, it's an interesting question because there's this period of so-called recombination 300,000 years after the Big Bang where you kind of can't see any electromagnetic radiation really prior to this because the universe is opaque and gravitational waves give a way to maybe peer past this. But I don't know necessarily what one might find there.
Yeah,
I want to get to one more question from Greg Weiss that has prompted some interesting discussion in the chat. Why is inflation needed? Why can't universal expansion of an isotropic low entropy state explain our observations? Graham.
Yeah, I mean, you have these regions that are like causally disconnected, which I think is the main kind of justification for inflation, right? And this is Matt is the one that can catch me up here, but bring me up here. But yeah, I think that I think it's just that the chances of it being isotropic, if you have these kind of quantum fluctuations that you require, that it's not smooth enough to explain this. I think, is that right, Matt?
Yeah. So when we look in one direction and we look as far as we can look, 46 billion light years in, that way, and then we look 46 billion light years that way, we see that those two parts of the universe are in, what you would call thermal equilibrium. Okay, so they have the same temperature now, the similar distribution of matter as you would only and could only expect from two regions that had been in contact at some point, so that they could distribute their heat and thermodynamic properties between them. Okay, so these two very distant regions clearly talked to each other at some point by exchanging energy and smoothing out. But if we just rewind the universe, based on the expansion rate we see now, they should never have been causally connected, and so so there's no explanation for why they should be so obviously once part of the same sort of very small system. There are a couple of other reasons. The other one is the flatness issue. So the idea is that the universe appears flat, spatially flat. The world is a globe, but the universe is spatially flat. And it's really hard to make a perfectly flat universe. It seems like a crazy coincidence that everything should be set up. You have exactly the right amount of balance, exactly the right balance between essentially expansion and the matter content to give you flat space. either of them tweaked slightly would give you strong curvature in either the positive or negative direction. Okay, so either the universe should be closed or it should be wildly open, kind of with this saddle-like structure. This is a hard one to talk about simply, but moreover, over time, any very slight deviation from flatness increases massively. Okay, so if the universe started very flat but with a slight curvature in either direction, then that curvature would enhance as the universe expanded. And so in order to see the flatness we see now, the universe at the beginning must have been insanely smooth, insanely flat. And one way to flatten a universe is with inflation. That's another thing it would have done. So you could have had a universe that was once all causally connected, allowing it to distribute all smoothly. And then you hit it with inflation, and that throws those causally connected regions into, you move them away from each other faster than the speed of light, and they no longer appear causally connected. But that same process flattens the geometry of space-time and can, it very nicely explains the universe we see right now. We have a whole playlist on dark energy, which I encourage you to spend way too much time delving through.
It's a really good series, the Dark Energy playlist.
So, on that note, we are out of time. So I want to thank Dean and Tambi for joining us on the Hangout. The Spacetime team, Mike, Grayson. Thank you, Graham, for joining us and calling in even though you have a cold. And Matt, thank you so very, very much. Everybody on the live stream, we really appreciate the questions. This was a smart chat. And, I just want to say this show is such a joy to produce. 2-something years in, it still feels fresh. And we have so much planned. And thank you all for supporting via the Patreon. It's got to be the best Patreon out there. So we'll look forward to checking in with you guys on the next one. And Matt, any closing thoughts or closing words?
Wow, on the spot. I am 10 minutes late for my department meeting with a bunch of
Get the hell out of here.
Crazy old
You're welcome, Matt.
And I just want to say it is worth it. See you guys later.
All right, bye everybody. Thank you so much.
Bye.